Jai Hind everyone. My name is Dr. Dibya Bharti. Today I am going to discuss circuit applications of Laplace transform. Subject name is Network Analysis and Synthesis with subject code KEC 303. So, in earlier discussion we had seen definitions of the Laplace transform, we had seen the properties of the Laplace transform. So, today we will see how we had also discussed advantages of Laplace transform, that why we are using this Laplace transform in circuit analysis, in network analysis. And then now today we will see the numerical example and a circuit application of the Laplace transform. So, first we will recall some of the basics, that these are the circuit applications where we can easily find out the transfer functions, we can find out the convolution integral, and also we can analyze RLC circuit with initial conditions. Okay, with the help of the Laplace transform we can easily include the initial conditions in the network. Okay, so if we transform the circuit from S domain, from time domain to S domain, so when we by using the Laplace transform we can directly transform circuit from time domain to S domain. Okay, so and when we transform circuit from time domain to frequency domain, resistance can be written as it is. Okay, R, and then L can be written as S into L, and C, capacitor, will be written as 1 by S into C. So, see, first is the transfer function. So, if this is the network, this is the input, xt is the input, yt is the output. Okay, and ht is the function, transfer function for the network. So, we can write in time domain ht, yt equal to ht convolution xt, but in S domain we can write ys equal to hs into xs. Okay, so easily we can find out the transfer function, that is hs equal to ys divided by xs. Okay, we don't need to go for the convolution. Okay, see, this is the example, first example. Here we will find out the transfer function. Here Vs is the source, 2 ohm and 1 Henry inductor is there. This is the 4 ohm resistor, and 0.1 microfarad capacitor is there, across which we are taking the output. So, this V naught is the output. So, we need to calculate the Hs equal to V naught by Is. Okay. So, as we know, what is transfer function? Transfer function is the ratio of Laplace transform of output to the Laplace transform of input, subject to initial conditions 0. Okay. So, here it is mentioned also here that we need to assume 0 initial conditions. Okay. So, now what we will do, we will transform this circuit into S domain. Okay. See, here what is this circuit is there in the time domain. Now, we can easily convert this into the S domain. Okay. So, in S domain, R is R, as we had seen, R will be R. Okay, L will be S into L, and capacitor will be 1 by S into C. Okay. So, here 2 ohm resistor will be as it is, inductor L of 1 Henry is there. Okay. So, we will write S into L, so S into 1, so S into 1. Okay. Again 4 ohm resistor will be as it is, and 1 by S into C. What is the value of C? C is the 0.1 microfarad. So, 1 by 0.1 into S. Okay. So, 1 divided by 0.1 into S, that is 10 by S. Okay. So, capacitance is there 10 by S. Okay, no, it is not capacitance here, it is the reactance. Now, we are writing the reactance directly. Okay. So, now Vs will be Laplace transform of this is written, and this is the Laplace transform of output. Now, we can easily apply KCL, KVL and find out the values, relation between V naught and Vs. Okay. So, now here what has been done by using the voltage division rule, here see, this is the input, this is the output where we will calculate the output. So, these two are in parallel. Okay. So, 4 parallel 10 by S. Okay. And what is the total current? Okay. So, total current is, as we can see, this is the 4 parallel 10 by S. Okay. and then this whole is in series with this, so 2 plus S. So this is the total, you can say, impedance of the network. So this is the ZS here. Now Vs divided by this ZS will be current. Okay, then you can apply the current division rule. Okay, so ZS, what is the, suppose this is the current Is. Okay, then what is the current here? So this Is will be divided here. Suppose this is I1s, this is I2s. Okay, so now Is, we can write Is as Vs as divided by Zs. Okay, and I2s is Is into 4 by current division rule, Is into 4 divided by 4 plus 10 by S. Okay, so now you need to write this value. Okay, and what is the V naught as? 10 by S into I2s. Okay, so V naught as is 10 by S into I2s. Okay, so now you just keep the value of 10 by S, and what is I2s? Is into 4 by Is into 4 divided by 4 plus 10 by S. Okay, so now put the value of Is. So what is Is here? Is is Vs by Zs. Okay, so Vs upon Zs into 4s divided by 10 plus 4s. So now this is V naught s. So now easily you can have the value of V naught s upon Vs. Okay, so now 10 by S into 4s upon 10 plus 4s. Okay, into 1 by Zs, and now you can keep the value of Zs. Okay, Zs. So this is the simple way for calculating the transfer function in S domain as we transform circuit from T domain to S domain. Okay, so this can be easily calculated here after keeping the value of Zs. So it is 20 divided by 2s square plus 9s plus 30. So this is the another question. Here see, dependent source is there. Okay, so now advantage of Laplace transform is that where in circuit if dependent source is there, you can easily transform that into also in S domain. Suppose what we are seeing here, this dependent current source is depending on current I. Okay, so when we will transform this circuit into S domain, we can write Is for this, then it will be 2 into, suppose Laplace transform of this is Is. Okay, so we will write 2 Is for this dependent current source. Okay, so when we are writing Is for this, then we can write 2 into Is for this. Okay, so simple. See here, circuit has been transformed. This 1 by S into C, 1 by S into C. So in place of C, if we write 1 by S into 0.5, okay, that means 2 by S. Okay, so this is 2 by S. Since we had written Laplace transform of this current as Is, so it is 2 into Is. Okay, so this will be S into 1. Okay, simple. This is S into 1. This is 3 ohm. Now just you need to calculate the V naught S by V1S. Okay, or VSS. Okay, so this is output. Okay, V naught S. So now you can easily find the value of this V naught S. See, V naught is 3 plus, see what is the value of the current here? This current is incoming. Okay, so what is the value of the current? 3 into I plus 2I, so that is 9 into I. Okay, so this is the V naught. Okay, so 3 into, what is the total current here? Okay, 3 into 3 is the resistance, and total I plus 2I is the current that is coming here. Okay, so this is 2I and this is IS. So 3 into 3 IS, that is 9 IS. Okay, so now what is Vs? In this loop you can write the KVL. So Vs is 2 by S into I. See, 2 by S into I plus S into S plus 3 into 3I. Okay, so this is the 3IS current is there. Okay, so if we write KVL in this outer loop, so 2 by S into IS plus S plus 3. S plus 3 is the total reactor impedance in this branch into 3IS equal to VSS. Okay, so and first equation that we had calculated here, that V naught is 9 into I. Okay, so V naught is 9 into IS. Okay, so Vs is from this equation, if we take common as IS, okay, so IS is 2 by S plus S plus 3. Okay, sorry, 3 into S plus 3 equal to VSS. Okay, so now instead of IS you can write V naught upon 9. V naught upon 9 is 2 by S plus 3 S plus 3. Okay, so this is the equation. Okay, so now instead of IS, V naught by 9 is written, so this is the Vs into S. Okay, so this is the multiplication of IS into 9. So now you are getting the relation between VSS and V naught. Okay, see, so this is the relation. So here first equation is now instead of I you can write 2 by S plus 3S plus 9, and instead of 9 you can write V naught upon 9. So now you are having the direct relation between Vs and V naught. Okay, so V naught as by V naught divided by Vs. This is 9S divided by 3S square plus 9S plus 2. So third example is that use convolution to find the V naught S. Now we need to find out the convolution. Okay, so here question is that use convolution to find the V naught T. We need to calculate the V naught T in the circuit given when the excitation is the signal that is shown here. Okay, this is the excitation. Vs is 10 e to the power minus t. Then we need to calculate the V naught T. Okay, so first what we will do, we will transform this circuit into S domain. So that is done here. VSS 1 2 by S. Okay, so now you need to calculate the transfer function, so that okay, so if you will calculate the transfer function, that is V naught S divided by VSS. Okay, so that is up you can apply the voltage division rule. So 2 by S, okay, 2 by S divided by 2S plus 1. So this is the transfer function. So after solving this, you will be having HS as 2 divided by S plus 2. This is the transfer function of this given network. Okay, so now you, if you need to calculate the output V naught T by using convolution, then you will have to calculate the inverse Laplace of this. Okay, so if HS is 2 upon S plus 2. Okay, so you can easily write 1 minus S by S plus 2. Okay, so you can write S divided by S plus 2. So okay, so this is the, now you will calculate HT, okay, by taking the inverse Laplace of this. Okay, so HT is 2 e to the power minus 2t into ut. So now from this relation, V naught is Vs into Hs. So V naught S is Hs into Vs. Okay, but V naught T is HT convolution V naught T. HT convolution VST. So you will have to calculate the convolution. Okay, so this is the way by which you can find out this integral, because ht you have calculated and vst is 10 e to the power minus t. Okay, so v naught vst, okay, see v naught, see here in question it is given vst is 10 e to the power minus t, vst is 10 e to the power minus t. So 10 e to the power minus lambda d lambda. So this is the integration of that, because we need to calculate the convolution of ht into vst. Okay, so this is, we had seen 3 example. Okay, so in 2 example we had calculated Laplace transform, we applied Laplace transform for calculating the transfer function, and in 1 example we calculated the convolution of 2 functions. So apart from the transformation, okay, we must model the S domain equivalent of the circuit element where initial conditions are involved. Okay, so in this circuit we had not we were not provided with the initial condition. In all the conditions, in all the example, initial conditions were 0, but we need to know the circuit element in S domain when there will be initial conditions. Okay, so except resistor, both inductor and capacitors are energy storing element. So these so it is important to consider the initial current of an inductor and initial voltage or charge across the capacitor. Okay, so for an inductor, if we take Laplace transform on both sides, see VL is L di by dt, so VLS is S into L IL plus this. Okay, so if we calculate the current, inductor current, so ILS is VLS by SL plus IL0 divided by S. So this is the initial condition. Okay, so now if we represent this with network elements, okay, so this is representing the current, this is the current, so this is also the, see here, so if we draw the equivalent circuit for this, so if SL, see VS, SL and L I0, if you will write the KVL equation in this, so we will find SL into IS minus LI0 equal to VLS. Okay, so now, so this is for representing for this equation 1a. Okay, so equation 1a is being represented in here, and if you write if you draw the, this is representing the current sources. So here this is the circuit for representing the equation 1b, that is Vs, Is current is there, SL is there, and this is the current source. Okay, so here if you write the nodal equation here, so ILS, this is the ILS, okay, this is a VLS basically. So ILS is SL, VLS divided by SL. Okay, and this is the, what is the current, this is the ILS is the incoming current, outgoing and outgoing. So ILS equal to VLS divided by SL plus this current. Okay, for capacitor also ICT equal to C dV by dt. So if you will apply Laplace transform in both sides, so you will be having this ICS equal to VCS divided upon 1 upon SC minus this. This is term for the initial current, initial voltage. Okay, so here it is representing the initial condition. Okay, so now you need to draw the equivalent circuit to represent these equations. Okay, so in similar way as we did in the case of inductor. See, this is the equation, this is the circuit where we are representing this equation VCS. See, VCS, see, this is the 1 upon SC, this is the VCS. Okay, so IC, this is the ICS. Okay, this is ICS into 1 upon SC plus V naught S by S equal to VCS. So now here if you will write KCL equation, this is the ICS, this is the VCS. Okay, so VCS upon 1 upon SC. Okay, this is the incoming current. Okay, so this is the outgoing current. Okay, so plus minus CVC naught equal to ICS. Okay, because these two currents are incoming, one current is the outgoing current here. Okay, so now here we will see example in a parallel RLC circuit where we will be having the initial values also. Okay, so here parallel RLC circuit is given where Vt and It is given. We need to calculate Vt and It. Okay, so this is V, this is I. Value of these need to be calculated. Initial voltage is given as 5 volt and initial current is -2 ampere. So initial current will be through the inductor and initial voltage will be across the capacitor. So now first we will transform this circuit. Okay, and now we will represent this circuit with initial conditions. Okay, so see, R will be as it is. Okay, so here current is there, this is the, so we will write Is, and for initial value, see, this is the initial value. Okay, Li0. Okay, so what is the value of Li0? So that will be 4 into 2. Okay, so minus 8 volt source is there. Okay, in similar way, this is the voltage VC0 and VC0. Okay, is given 5. Okay, and this is the value of the capacitance, that is 1/80. Okay, so it is 16, 1/16. Okay, so now this is the transform circuit where these sources are there due to the initial conditions. Okay, this voltage source is there due to the initial current that is given in the question, and to represent that initial condition, and this current source is there to represent the voltage that is there with the initial condition. Okay, so now this is the transformed circuit in S domain. So now using nodal, what you need to calculate is that Vt and It. So now see, now here nodal analysis has been applied. So I plus V divided by 10 parallel 80 by S minus 4S minus 1/16 is 0. So now using this, V has been calculated. So V is 5S plus 96 divided by S square plus 10S plus 20. Okay, so now since it cannot be factorized easily, okay, so you need to write the completion of the square. Okay, so we need to calculate the voltage in time domain. Okay, so now Vs is there, 5S plus 96, S plus 4 square plus 4. So now this is the partial fraction, you can say, okay, of this term. So now you can find the inverse Laplace transform. So Vt will be 5 cos 2t plus 230 sin 2t. Okay, ut. So now It will be V minus 8 by 4S. Okay, It will be V minus 8 divided by 4S. So V minus C, V is the voltage, minus 8 divided by 4. So here V minus 8 by 4S. So in S domain we are having the value of V. So now if you will keep this, you will this is the value of current in S domain. So now again you will have to calculate the inverse Laplace. You will have to find the inverse Laplace. So you will have to use the partial fraction for solving this. So this is the way here Is can be written as the partial term. Okay, so you will have to calculate A, B and C by using the partial fraction rules. So A can be calculated as 6, B as -6 and C is -46.75. So now if you will put these value, so you can calculate the It. Okay, so this is the value of the It. Okay, so this is another example. Here switching conditions are there. Okay, according to switching condition, you will have to analyze the initial condition by yourself. Okay, so here initial conditions are not clearly mentioned. Question is that the switch is in the following circuit moves from position A to B. Okay, initially it is at position A. Okay, so and after some at t equal to 0, it will be moved from A to B. Okay, so this is t equal to 0. So now see, 24 volt source is connected with 5 ohm, and these two are there in parallel. Okay, this inductor and capacitor is there in parallel. So when switch will be moved from A to B, then source will be disconnected and these two will be connected with this part. So calculate I naught t. Okay, so now when this source is connected with this for long time, this inductor will behave as short circuited and capacitor will behave as open circuited, okay, in steady state. So since it is connected with A, so we will assume that it has been achieved, it is there with the steady condition. So now this is the initial circuit where inductor is behaving as short circuit and capacitor is behaving as open circuit. So by visualizing this, you can easily find out the IL. So it will be 24 divided by 5. So initial current through the inductor is 4.8 and initial voltage across the capacitor is 0 because it is behaving as open circuit. So these are the initial values that you have calculated according to the given condition. So now switch has been moved from position A to B. So in that case, this part will be neglected and this part will be there. So now inductor will be represented with initial condition in S domain. Okay, so this is capacitor and this is the resistor through which you need to calculate the current. So now simply this is the only source here and these are the reactances and this is the resistance. So by applying current division rule, you can calculate this easily. Okay, so what is the total impedance? Total impedance of this circuit is 0.627 S plus 10 by S parallel 1. Okay, so now this is the total current minus 3 because direction is opposite. So minus 3 divided by, here current is leaving the negative terminal of the source. So that's why minus 3 divided by 0.625 S plus this, and this is the value of total current. So now this total current will be divided into part. So by applying current division rule, you can find out the value of I naught. So I naught is this. Now apply partial fraction and then apply inverse Laplace transform. Okay, so see, this is the total current and we are applying the current division rule. So 10 by S, since we need to calculate the current through this, so 10 by S divided by 10 by S plus 1 into I. So after keeping the value of I, so this is the value of the current I naught. Now this is simple, we can calculate the IT by partial fraction. So here after partial fraction, this is the value of I naught S, and if we apply inverse Laplace transform, this is 8 into e to the power minus 8t and it is e to the power minus 2t. So this is the way by which we apply Laplace transform to the circuit for calculating transfer function, for finding the convolution integral, and for finding the solution in the circuit where initial conditions are there. Okay, so thank you all.